In this video, we're going to talk about the noise performance of entire receiver chains. I've drawn a receiver chain here that shows the noise sources of each amplifier stage. Note, this is a pretty simplified receiver chain. Most receivers would need transmit-receive switches, filters, mixers, and other components, and we'll have more notes on those soon. We can calculate the noise temperature that the first amplifier emits by referring T in and T1 through the power gain of the first stage. That output noise becomes the input for the second stage. So the output noise of the second stage is given by referring the output of the first stage plus the temperature of the second stage through G2. This means T in and T1 have an amplified impact on T out 2 because they've seen two gains, while T2 has only seen one gain, just G2. If we follow this through every stage, then we finally come up with an expression for the total noise voltage variance of our system. It consists of a thermal noise term and a quantization term. The thermal term is a big effective temperature that's multiplied by K and some assumed bandwidth B and 4R to convert it to a voltage variance. Then we add that voltage variance to our quantization term, which is also a voltage variance. This expression shows us something really important about receiver design. The noise of the first stage matters much more than noise in later stages. We can see in this effective noise temperature the T in and T1 terms both see the full gain of the receiver, while T2 and T3 see much less gain. We can't do anything about the input noise temperature. It's part of our input signal, so we couldn't separate it out or design around it. But we can do our level best to make T1 small. This concept is so important that there are a special class of amplifiers called low noise amplifiers, or LNAs, that are used as inputs of receivers to minimize the noise contribution of the first stage. The quantization noise term in this expression is also interesting. It isn't multiplied by the gain of receivers, so this noise term doesn't get bigger as gain increases. That means making a signal bigger will make quantization noise a smaller fraction of the total signal, which answers the question of why we use amplifiers. We make our signals bigger to overcome quantization noise, and we sacrifice some signal-to-noise ratio to thermal noise to do so. Our receiver model, which is pictured on the top of this slide, is kind of complicated. There are a lot of noise sources in it, which might be an unnecessary level of detail if we're not trying to optimize the design amplifier by amplifier. So we can make an equivalent model that just lumps all the noise sources at the end of the receiver chain. From the perspective of the ADC, these two chains are identical, but the designer can think less about the version with the noise at the output. This model is called an output-referred noise model. Another popular simplified noise model involves referring the noise of the amplifiers to the input. This noise source that lives at the input is called the system temperature. System temperature is popular because you can calculate your SNR very quickly if your gain is high enough to ignore quantization noise. Finally, we can use the output-referred noise to derive a cascade formula for noise factors and amplifiers. I don't love using cascade formulas, instead usually prefer keeping a spreadsheet of the noise level at every stage, but these are good formulas to know about anyway. We can calculate the total noise factor for this amplifier chain using the output noise temperature and the total gain. We're ignoring K and the bandwidth in this equation because they would fall out of a ratio of noise temperatures. K and B would be both on the top and the bottom of this expression. And as usual, we split our SNR calculation ratio into a ratio of signals and a ratio of noises. The output signal is bigger than the input signal by the total gain, and we compare the output noise here to an assumed input noise of the physical temperature. Canceling gains cleans this up significantly. And finally, doing a little bit more cleanup leaves us with the cascade formula for noise factor. Confusingly, this is called the freeze formula, just like the path loss formula is, so you just have to know from context whether people are talking about path loss or the noise factor of cascaded amplifiers. This formula also emphasizes how important the noise performance of the first stage is to the behavior of the whole receiver. We see all of NF1, while NF2 and NF3 are discounted by the gain of preceding amplifiers. So in summary, the first amplifier in the chain, which is often called the LNA or the low noise amplifier, has the most impact on the total noise of the system. Gain can reduce the relative effect of quantization noise on SNR. Noise temperature can be moved around. It can be input and output referred. And in particular, system temperature is input referred noise from the amplifiers.